I left home for a little while to go do my PhD in artificial intelligence at the University of New Hampshire. Since then, I've been working on static analysis, logistics, planning, and scheduling for a variety of concerns. And now I'm back here in Indiana as a senior software engineer for SEP. So today we're going to talk about a few different things. We're going to start with what heuristic search is and why you should care at all. After that, we're going to go through a single heuristic search algorithm from like the very basic implementation to something that might actually work at a problem of scale. So if you've never seen heuristic search before, which I suspect is true of most folks, hopefully you'll get a handle on what it is and what it can solve. So search, despite what you might believe as a result of search giants like Google, is actually a technique for solving problems rather than a thing for information retrieval, at least in the world that I'm from. So search problems look a certain way. Here's an example heuristic search problem. I am over here in this grid world, and I would like to get beer. So I would call this particular configuration of the world a state. So it's just some set of situation, right? I'm here, and the goal is over that way, the beer. And there's some obstacles in my way, so I can't go right there. Search problems tend to have actions as well. So in this particular state of the problem, I could move to the north. I could move to the south. I can't move to the west because I'll go off the edge of the world, and that would be bad. I can't move to the east because it'll take me into a wall. There are goals in heuristic search problems. The goal for this particular instance is shown here. It's where I'm in the same location as the beer. And you can see that I think this is a green line. So there's a green line from where I originally started, that state, to this particular state, which is a goal state. And it shows the actions that I would have taken to navigate from here to there. So that's a solution to a search problem. And then these are heuristic search problems, so there are heuristics involved. And heuristics are simply things that tell us about how we might solve the problem. So for this grid navigation problem, we use what's called Manhattan distance, which is literally displacement in x, so the horizontal displacement from me to the beer, and the vertical displacement from me to the beer. So the heuristic of this state would be three actions. And it would, in fact, correlate to east, east, north. So search is cool because it's a general problem-solving technique. You don't really care what problem you have, so long as you can cast it in this particular world of states, actions, goals, and heuristics. So we showed you solving this grid navigation problem. Later, we're going to talk about pancake flipping over here and the traveling salesman problem, which are heuristic search problems that are pretty classic. You can also think of things like solving a crossword puzzle as a heuristic search problem. It's a specific kind called a constraint satisfaction problem. And then there's two-player game tree search, like you would see in chess or in Go or in Othello. Those are also kinds of heuristic search problems. So the other thing is that heuristic search is a technique for solving hard problems, and I mean that in the formal sense. I think we're probably all a little bit removed from our theory of computation classes. So what I in particular mean is that these problems are NP hard or worse. They are, formally speaking, intractable. So there's no good domain-specific solution that exists that can solve them in polynomial time, and there probably isn't going to be one that's found ever. To give you a more graphical representation of that, so informally, NP hard problems are real expensive, and we don't know good, cheap solutions. In particular, so one algorithm you've probably encountered in your life is selection sort. It's a technique for sorting lists, right? And it's polytime for an input size n. In fact, it's n squared, or n squared log n. Depth-first search is not polytime, it's exponential. So for a particular problem with a solution at depth n, it's actually the branching factor of the tree, and we'll get to what this means, to the n. So if you look at these two lines, x squared grows this way, and 2 to the x grows much steeper. And that's the problem. As the problem size increases, the cost of finding the solution grows really, really fast. And so if you care about problems of any particularly decent size, you'll never be able to allocate the appropriate amount of resources to solve them. Except that I'm going to spend the rest of the time telling you that that's actually not true. Yeah, so Those particular problems up on the board now are known to be NP-hard. The TSP for certain restrictions of the problem is known to be NP-hard. Stacking pancakes, the first example we'll go through, that's known to be NP-hard. Crossword solving, that's also known to be in that class of problems. So that's sort of what heuristic search is and why I hope you care about it. General problem-solving technique for things that are known to be intractable. Where we're going to go is that heuristic search can be really expensive. So checkers is a great extreme example. There's a guy named Jonathan Schaefer who maybe starting in 1989 set out to prove that checkers was a draw or a win or a loss for the starting player. Turns out it's a draw, and he ran a computation from 1989 to 2007 to prove that that was the case. So, using 200 processors, it took him on the order of 20 years. That's the most expensive application I know of. Things like very large systems integration, so that stuff that lays out the traces for the circuit boards on your phone, and the traveling salesman problem, those are hard problems to solve for heuristic search. You're talking about hours to days of compute time for moderately sized instances, like 3,000 cities or 3,000 pens. Scheduling, like is done for Major League Baseball, or to lay out classes for a school. This is a simpler problem, but given depending on the size and the constrainedness of the schedules, whether or not these two classes are allowed to be across from each other and so on, you could talk about solving times in the hours or days time frame. And that's probably not something you're willing to tolerate. Most of us don't want to wait hours or days for a solution. We'd like it now. Mercifully, compute time and wall clock time are different beasts. So I can throw a bunch of systems at the problem and get my answer in a time that I experience is very short, but which is actually, hours or hundreds of hours of compute time. I just have to be careful about how I slice the problem up. So the simplest approach to distributed heuristic search looks something like this. We talked about search states and applying actions to search states. And so you might think of that, that is a thing in search that we call an expansion. So a state and generating all of the places you can reach from that state, that's an expansion. That's the fundamental unit of work of heuristic search. So you might do something like this. You might post a node to S3 and have a Lambda waiting and looking for nodes to be posted. And then it says, oh, hey, a node showed up. I should do something about that. Well, did it represent a solution to the problem? Great, I'll report it. Oh, no, it didn't? Well, let's post all of the successor nodes. And you could do distributed search in this very simple fashion, except that you probably can't afford to for problems that you might care about. So one of the instances I was looking to solve for demonstration today was a 115,000 city traveling salesman problem. There are, as of 2000 or so, roughly 115,000 things that are considered cities in the US, in the continental US. So let's say we wanted to visit them all in the shortest tour. Well, basically what you're considering is all possible permutations of 115,000 cities, and that's this number, 115,000 factorial, potential solutions. If our heuristics are good, maybe we'll prune 3/4 of all possible states we might consider over the course of the search. That would be a great day. That's still this ridiculous number of expansions, 10 to the 500,000 or so. Well, how much would 10 to the 500,000 Lambda calls cost? More than the GDP of Earth for the next 1,000 years, or 10,000 years, or 100,000 years. It's an impractical number of function calls to make. So instead of turning every expansion in a search algorithm into a Lambda, we'll do something a little more restrained. We'll have something that tells a master about a new problem. That master will set up a bunch of worker nodes and will communicate portions of the work off to the worker nodes so that we can slice up the problem intelligently. And then rather than doing a single iteration of search themselves, they'll do a couple 100,000 or a couple of million iterations of search, then tell us about the solutions they found, and we'll communicate that back up the chain. So that's where we're headed. But first, let's talk about the thing that we're distributing, which is depth-first search. So this is the textbook definition of depth-first search, from artificial intelligence to a modern approach. This is the Python implementation that they give. And so they say what it does is it search the deepest nodes in the search tree first, search through the successors to find a problem goal. So what we do is we have a frontier. It's literally a list of search nodes, a list of those states that we saw on the first slide, or first set of slides. So long as the frontier isn't empty, take a node from the front of it. If it's the solution, report it. If it's not the solution, well, then we extend that node by each of the possible actions in that node and pop them back onto the frontier. Now, they call out here that there are some problems with this algorithm. In particular, in the event of loops in a search state, that'll go on forever. So let's fix that. So just as before, as long as the frontier is not empty, we'll take a node from the front of the frontier. And now we'll say, have we seen this state before along this particular path of actions? If so, throw it on the floor because it's not useful to consider anymore, and proceed as before. So that's, it's all well and good to say what the algorithm is, but let's look at it in a very concrete way. We're going to look at the pancake flipping problem, which is a sort of comical domain. So let's say that I'm entertaining, and I want to serve a whole bunch of my friends pancakes. So I throw some batter down on the griddle, I fry up some pancakes. They're of different sizes because I'm imperfect as a human. And I want to serve them to my friends, but I want to serve them in an appealing way. So what I want to do is I want to take this unordered stack of pancakes and flip the stack over repeatedly until they're in sorted order, because I don't want to just, touch the pancakes. That would be unsanitary. So for this particular problem, what we would do is we would insert a spatula here underneath the third pancake, and we would flip. And that would result in this state. And then what we would want to do is we would want to insert the spatula under the second pancake and flip again. And that results in the following state, which is a goal to our problem. So hopefully this ties back to the original grid world navigation problem, right? I have a state, and it is the situation of pancakes. I have some actions, and it's where do I insert the spatula to do the flipping. I have some goals, which is this lovely ziggurat of sweet cakes. And I have heuristics, which are things like how many pancakes are out of order, or how out of order are the pancakes that I have. So believe it or not, the pancake problem is known formally to be hard. There's a reduction from it to 3 sat. And if that means anything to anyone, I would love to talk to you after the session, and we'll go through it. But what it means is that we can reduce it to a problem we know is formally hard. What do I have here? I have the search algorithm again for reasons that are unclear to me. So that is the algorithm we run on a pancake problem. Here, we see the output. So I have some problem. It has 4 pancakes, and its initial state is this. The largest pancake is on top, then the next, and so on, right? And we produce a solution down here. It's this list of ordered lists of numbers. It just shows the states that we went through to get to an answer. So we can actually solve an NP-hard problem using depth-first search in the way that we just described implemented in Python. However, it doesn't scale. So this is a plot of solving time for 100 consecutive instances of the pancake problem generated randomly. For very small stack sizes, like 2, 3, 4, we take next to no time to solve the problem. But as we transition from 7 pancakes to 8 pancakes, all of a sudden we go from taking seconds to taking hours to solve hundreds of instances. And that's because of this exponential explosion in the size of the search space. Remember that these problems take time exponential in the length of the solution to find, and as you increase the number of pancakes in your stack, you increase the average solution length, and so you increase the average solving time. So we don't want to do that. And why does this happen? It's like, well, we just throw the children. So when we take a node and we generate all of its successors, I will refer to those nodes as children nodes because they have a parent-child relationship in the tree. We throw all of those children onto the frontier all willy-nilly. We don't order them. We don't have a favorite child. And you really can't do that in heuristic search. So considering the child orderer is critical. So let's imagine that this is a caricature of a search algorithm running on a problem. The first state that we consider is up here, and then we generate all of these states, and we select this state off the frontier to consider, and so on and so forth. So before you consider the second child of the root node, you have to go through all of this work. So I have to enumerate all of these nodes over here in red before I'll ever go back and consider this node up here. And if all of my solutions lie underneath here, that's a problem. And this is for a branching factor of 3 and a depth of 5. If I have a branching factor of 115,000 and an average depth of 115,000, like I do for that TSP problem, I'm well and truly hosed. So we're not going to do that. We're going to sort the children, and we're going to sort the children right here. So we order the children based on some heuristic, which I won't go into, but we can talk about later. And then we put the children onto the frontier in such a way that we'll consider the best child of the current node first. And that ends up being a huge savings. Another thing that we need to do, or that we are doing in this algorithm that we shouldn't do, is we generate all of the children at once. So it's not necessary to expand all of the children of a node at once if we're only really going to examine the best one first. And you can realize a bunch of savings that way. So again, we have this caricature of search tree. If we greedily expand all of the, or eagerly, I should say, expand all of the nodes, we end up with an image that looks like this. But if we're careful and only keep the nodes in memory that are part of our avenue of investigation, so from the root to the current thing being considered, then we can have a lot of savings. We don't actually need to keep these guys that are the dotted lines in memory anymore. We just need to consider this small line. And that can be, it's the branching factor effectively to the depth in savings. It's exponential savings we're realizing. And that's not just in terms of memory consumption, it also takes time to generate these nodes. So we save ourselves the effort of doing so up until the point where we actually need to consider them. So we alter our Python a little bit more, right, to do some bookkeeping. So now not only do we know about the node that we're expanding, we know which child of that node we considered last time. We walk up and down the tree, incrementing the child being considered until we exhaust the tree. Using those two optimizations only, we now get this kind of performance on the Pancake problem. So again, we're looking at time to solve 100 instances in seconds. On the x-axis is the number of pancakes that we're using to define our problem. And you see we're talking about solving 7, 8, up to about 20 pancakes in a tens of seconds scale, which is way, way, way faster than the hours we were taking before we did these two very simple optimizations. But we still run into this exponential complexity over here after we scale out past about 20 pancakes. We're saying, well, it still takes us tens of minutes to sort the stack of 28 pancakes. Now, maybe you're only plating 20 or 25 pancakes and that's not a problem. Maybe it is. The other thing to note, though, is that I'm lying to you about the performance here. And I'm lying to you because of this word. So I'm saying it takes us 10, 15 minutes to solve the problem optimally. I find the cheapest solution to the problem, or at least a solution that is no more expensive than any other solution to the problem, in the case that there are multiple optimal solutions. Now, you probably don't need the optimal solution in all of your settings. If you're doing an industrial process where you're running the same solution 100,000 times, you absolutely care, because you want to get the optimal solution so that you realize that savings from the computation every time you run it. You can recuperate your costs effectively, amortizing them out over the number of times you use the solution. So really, the performance of depth-first search on a given problem looks more like this. So on the y-axis, we're showing the cost of the solution that the algorithm has found so far. And on the x-axis, we're talking about how long it took the algorithm to find that. So for a 200 pancake problem, now not these wimpy 20 pancake things from before, we find our first answer, in tens of seconds. And over the course of about a minute, we have the cost of it. And if I were willing to spend more computation, I could reduce the cost even further, eventually converging on the optimal solution. It turns out depth-first search is usually also referred to as depth-first branch and bound, and it is an anytime search algorithm. What that means is that at any time you can interrupt it and consume its solution, and eventually it will converge on the optimal solution. So we come back here to our friend, the caricature of the search algorithm, and let's say that it's always expanding the leftmost child because it thinks the leftmost child is the best child. It will run down here into this solution and report it. And then it will walk back up the tree and consider these nodes, and eventually it will run into this solution, represented by this star here, and report that one. And then it'll get up here to this one. And as long as we do some clever things about pruning nodes based on their estimated cost or actualized cost up to this point, we can guarantee that we get that nice little plot from before where we get some initial solution deep, deep, deep in the tree, and as time progresses, we always report a better and better solution so that we can consume the best one that we have at any time. Oh, I had it in front of me too. So that's the Pancake problem. That's one application of depth-first search. It's a very simple problem. I like to start with it. The TSP, the traveling salesman problem, is more like an industrial problem because it maps directly to logistics problems. It maps directly to VLSI, to ramming grommets through a piece of fabric, all sorts of interesting industrial processes. But let's go back to the Pancake problem. So I'm going to make 200 pancakes. I just don't have that much Bisquick in my house. So I live here, and these red dots represent a bunch of grocery stores in the area. And I'm going to go over there, and I'm going to buy my pancake mix. Well, I want the shortest possible tour to take me between my house and all of the grocery stores. And let's say I start with a greedy solution where I drive to the next nearest grocery store every time. I get this gnarly-looking tour here. And you can see it's bad because you can see it crosses itself in a bunch of places. But if we let heuristic search run on and on and on, eventually we'll produce this, the optimal tour of all grocery stores in the county that I don't live in. But, you know, hypothetically. So what I think makes heuristic search so cool is that you can take the same solving algorithm, depth-first search. I don't have to change it at all. I just have to change the definition of the problem I hand it. And if you can see the source code that's up here, it's written in F#, so bear with me. But the notion is that I define my problem in terms of some initial state and some goal test and some heuristic functions and some way of generating the successor states. And then I feed that into a search algorithm. And down here, I do exactly the same thing. I define my problem in terms of heuristics and goal tests and successor functions, and then I hand it into a search algorithm. And this one on top, I believe, happens to be this one is the TSP, and this one is the Pancake problem. But they don't really differ in structure at all. It's just what I happen to feed the algorithm as its solving steps. So the TSP, we'll just go straight into the anytime performance. So let's consider a problem with 237 cities, which is small for the literature on the TSP. We're starting off with a tour cost of roughly 1,400 miles, and we're ending up with a tour cost of about 1,280 miles. And we get to this, eventually we'll prove the solution is optimal, but so we get to this not known optimal solution in about 4 seconds. And then after a few minutes have passed, we prove it's correct. If we ratchet up the number of cities, now we're starting to talk about tour costs in the 3,000s, and over a minute or so, we get it down to still in the 3,000s, but we've saved ourselves a little bit. The important thing to notice here is the steppiness of the solutions. So we get a good solution, and then for a long time, we don't improve it, and then it jumps. And then for a long time, it doesn't improve, and then it jumps. And then for a long time, it doesn't improve, and then it jumps. So what we'd really like to do, we can't do much about how long it takes for this first solution to arrive. That's sort of a fundamental limitation of the problem, unfortunately. But we'd like to reduce the space between those solutions. And the way we do that is by throwing gobs and gobs of compute power at the problem. So Depth-first search is particularly interesting because of the fact that it's a tree enumeration. And because it's a tree enumeration, it parallelizes really, really well. So we go back to our caricature. Well, on a given spine of the problem, right, from the root to a node we're considering, it turns out that really all of these nodes in yellow are kind of unrelated. They're related in the sense that they come off of the root of the problem somewhere, but the computations that go on beneath these nodes are disjoint from one another. And so I expect another node there. So what we're going to do is we're going to take some initial process, expand the tree out to a certain depth, and get a pile of nodes to divide out amongst a bunch of workers. So it looks kind of like this. We have some executor. They expand out until they generate all of those nodes in yellow. And then they communicate those nodes to a set of workers, or they communicate several things to a set of workers, but among them is those nodes. So one of the things is the executor will say to the worker, hey, I've got a new piece of the search problem to work on. Please solve it for me. It might tell the subprocess to fall over entirely so that we can kill everything and exit cleanly. Alternatively, it might say, hey, I know about a new best solution to the problem. Don't consider anything that's particularly bad right now. Nothing worse than the thing I already know is good. Similarly, the workers need to talk to the executor. They need to say to the executor, hey, I know about a new answer. Please incorporate it and tell everyone else for me. They need to be able to tell us how much they've spent solving the problem. They don't really need to be able to tell us this, but if we want to know how much we spent after the fact, it's useful to have that information. And of course, if they've exhausted a subproblem, then they need to tell us about that so that we can give them new work. So now what we're going to do is, we're going to consider, so we're going to do this in parallel first on a single machine. And our budget is going to be limited based on our hardware. We only have so many cores. We're probably only going to run 1 or 2 threads a core. So what we're going to do is we're going to hand these 2 green nodes to a processor, and these 2 other green nodes to a processor, and these slightly different green nodes to a processor, and so on. So it's not as bad as you might think in terms of distributing the search code out. It's not Python anymore. It's a different programming language, but the notion is the same. We have some sort of message coming in from the executor, and it tells us what to do. It says, oh, there's a new incumbent cost. Well, I'll incorporate that in my search algorithm. Oh, I'm supposed to stop. Well, let me. Hey, here's a new problem for me to work on. Great. My frontier, or my open list, is now just that node, and I'll go from there. And then after I've processed some messages, I'm just going to run the search for a few iterations, and I'm going to see if I have new messages to process. So it's exactly the search code from before, except every 100 steps, every 1,000 steps, in this particular case, every 10 steps, we stop and we ask if the thing that's coordinating our work with other people has given us new information to process. Let's skip that. Where's the rats? So this is the executor setting up all of the work. So it expands some nodes in the search tree, it stands up some workers, and it sends them their initial messages and processes its messages here. But the thing that's really exciting is not doing it on a single machine, but doing it on a couple of hundred or a couple of thousand machines in parallel. So, the first thing we did was we distributed it exactly in this way, right? We have the executor, we have some workers, and we have some messages that go between them. We're going to have to add a little more infrastructure. And that infrastructure looks a little bit like this. So a user hands us a question, which is a search problem of some variety. So it's both the domain definition, which is, here are the actions, here are the heuristics, here are the goal tests, and an instance. So here's a particular situation of the world I want you to start from. That goes into a dispatcher, which posts the problem and a budget to the executor. And the executor uses that budget specifically in terms of compute nodes to spin up however many workers it needs or however many workers it's allowed to, generate work for them, and then parcel it out. To give you a very specific breakdown of how you might do this, one way you could do it is you could use lambdas for the whole thing. So you've got some S3 events over here where you're posting the instances. You say, oh, someone wrote an instance to an S3 bucket, and then I'll spin up a new Lambda based on that. So the dispatcher says, oh, I'll just post this instance along with its budget as a JSON object or something, and then the executor will know to pick that up. The executor will pick it up, and it will say, oh, okay, I have a new instance. Let me generate some nodes. Let me post those back in such a way that they're picked up by workers and that they produce their solutions, and I'll know how to process those. Now, you could do this with S3 events. You could use simple notification service. You could use whatever your favorite message passing interface is. It really depends on what your backend looks like. The thing I will note, though, is that for the search problems that I was interested in solving, I found that the 15-minute hard limit on Lambdas was insufficient for what I wanted to compute. So I could have done some fun things where I parked the computation and then picked it back up later so that I could actually effectively run for hours on Lambda. But in practice, what worked better for me was to take those things to EC2 instances, or in actuality, I did the whole thing on DigitalOcean. But what I really did was I span up a bunch of compute nodes, told them where each other lived, and then let them do their message passing via MPI. It doesn't change very much about the architecture, though. So there's a provisioner that's now in the way that spins up my instances for me and puts the problem in the right place on the hard drive and runs the right script. But other than that, very little has been changed. I really thought I had some performance notes in here, but apparently I don't. So at this point, I'm at the end of the less technical content, and I'd love to take some questions. If there are none, I'll go through some very interesting proofs of why the problems are optimal. So that's what's on the other side of not asking me questions. Yes? So in practice, as I said, it's mostly DigitalOcean, so it's a bunch of bash scripts that spin up instances for me. I should repeat that question. How did I do it? It's a bunch of bash. How do I provision the instances? It's a bunch of bash scripts. It's a big pile of bash. All right. Yes? No? No? Okay. You moved. I was excited. All right. So we talked a little bit about what optimal was, but let's be a little more specific about it. So informally, optimal solutions are the best solutions to a given problem. But formally, they mean this. Let's say that there's some goal test which we need to define the search problem, and it's being applied to some node n. So let g of n be the cost of arriving at some node in that problem. So it's from the root, I applied all of these actions. What's the sum of their cost? So there's some graph, script G, that is the potentially infinite graph induced by the search tree. So taking a node, applying some actions, taking that node, applying some actions, and so on. So if that graph exists, then the set of all goals is defined to be those nodes in that graph such that they pass the goal test, right? And then the optimal solutions, or the optimal goals, are those nodes in the set of goals such that for all other nodes in goals, they have a cost that is no larger than that other cost. So literally, it's any node any solution whose cost is not larger than that of other solutions is defined to be optimal. There's nothing particularly scary here. We can do interesting pruning based on optimal solution cost, or based on incumbent cost to converge on the optimal solution. So I skipped over this line previously. If the node that we have in hand is better than the solution, or rather, if the solution is better than the node, keep going. So this is actually where all of the efficiency in depth-first search comes from. You find some answer, you throw away everything that's worse than that answer, rather than considering it. Well, how do you do that? So depth-first search converges on optimal in part because it does this, right? So it has this test which forces all nodes that it considers to be no worse than the current incumbent solution. And every time we find a solution, it satisfies this predicate. And so we exhaust the entire search space. So we must ultimately converge on the best solution because we threw everything else on the floor. No, I don't want to go through the exact definition. Yeah. So we prune on a quantity called f. So f is an amalgamation of two values. It's the cost of arriving at a node, and it's an estimate. This is the heuristic portion of the problem. It's an estimate of the cost of solving the problem from the current state of affairs. And importantly, it's a lower bound on that problem. We'll need some other things to prove some stuff. Specifically, we'll need h star, which is an oracular version of h. It's God himself has come down and told us the solution costs this much from this point, no more. So it turns out that h of n is a lower bound on this value, and so we can do some fun stuff. We say, well, f of n is the quantity g of n plus h of n. F star of n is g of n plus h star of n. So literally, this is our lower bound on solution cost. This is the true value of solution cost. Well, it happens to be the case, because of how h is defined, that our lower bound on solution cost is no larger than the true value of solution cost. And because of the way we expand nodes, it's no larger than the true value of the solution we have in hand, which is just the true value of the solution we have in hand. And as a natural consequence of that, it is true that if a node's f of n is larger than the cost of the incumbent solution, we can discard it. And that's how we are able to throw away so many things and still converge on the optimal solution provably, which is a pretty cool consequence of the heuristics, their properties, and the inequalities here. I don't want to talk about the TS, and we already talked about how it's domain enough. Now I'm truly out of content, so I thank you all for your attention.